It's hard to believe, but this is actually week 5 for remote learning. We will focus on projectile motion this week. What that means is we'll be modeling projectile motion, still using quadratic equations. Projectile motion could be something like the path of a football being kicked or a baseball being thrown or any object, something like that. Your homework this week, Coach Warden has designed a Desmos activity instead of doing a Canvas quiz, just trying to do something a little bit different for you guys. Just a reminder, like it has been each week, we have office hours from 1 to 2, Monday through Friday. Again, didn't hear from many of you last week. If you're struggling, please let me know. I'm happy to help. All right, so I think I mentioned talking about a baseball. So in this example, it says a baseball is popped straight up by a batter with initial velocity of 64 feet per second. The height of the ball above ground is given by the function y equals negative 16t squared plus 64t plus 3, where t is time in seconds after the ball leaves the bat, and y is the height in feet. Although the path of the ball is straight up and straight down, the graph of its height as a function of time is a parabola. The ball goes up fast at first and then more slowly because of gravity. So from that information that I read, if you look at the equation that's here beside the picture of the parabola, you may notice some of the numbers, or at least one of the numbers represented. In the problem, it talked about 64 feet per second. And if you notice, that shows up here as the coefficient of the t. I believe that's the only piece in that paragraph that it shows. So we'll talk about the remaining parts of the equation in just a minute. If you look at the picture, and again, this has already been graphed for you, you could graph this using Desmos, or for those of you that have your own graphing calculator at home, you could set up your window to match this picture. But if you notice here, it talks about the initial height being 3. So I'm going to highlight that here, this initial height of 3, and we can see that shows up in the equation as the constant. Just a reminder, the constant is a number without a variable. And then the only number that we have not talked about thus far is that negative 16. And that negative 16 that we see there is actually gravity. So the 3 is our initial height. The 64 is our initial velocity. I'm just going to draw an arrow up to the paragraph. Again, where we had talked about it being initial velocity. Just so that you kind of see where those pieces come from. Now, if you are graphing this in your graphing calculator, instead of using the letter T, you will use the letter X. Again, they've used the letter T to connect it with the word time. So what I want to do is look at the questions on the right side, the letters A, B, and C, and we're going to mark those in the graph. I'm going to use red for that just to make sure they show up and stand out to you. So these are some of the typical questions that you will be asked in the examples today and on assessments. It says, what is the initial height of the ball? Draw a circle at this point on the graph. So again, if you think of the word initial, I did this a lot in class. I would say, initially, how old were you? So this initial is when time is equal to 0. So in other words, your y-intercept. So I kind of drew a circle already, but that was the spot there. So that is our circle. That is going to be the initial height of the ball. So the ball goes up in the air and then it comes back down. So for part B, it wants us to draw a triangle at the point on the graph where the ball will hit the ground. So I'm going to draw a triangle here showing you that height is 0. So that spot ends up being an X-intercept. So just making some notes here to connect this with prior weeks of remote learning. And then lastly, we're supposed to draw a square where the ball reaches the maximum height. And then another question that they typically ask of that is, what will the maximum height be when the ball gets to that maximum height? So when does it get there and what is the height? And so that's our vertex. Let's see if I can do that a little bit better. Our vertex up here at the top of our parabola. So again, making notes here to help you remember how do you find these pieces. So again, this was just kind of an introductory slide to show you what the graph will look like of this quadratic equation and seeing that parabola where it's modeling projectile motion. All right, so some examples. It says an object is launched directly upward at 64 feet per second from a platform 80 feet high. The path of the object can be modeled by the equation h of t equals negative 16t squared plus 64t plus 80. There's a little block here, and this is more of what I would have used had we been in the classroom together, but it talks about setting up your window and what some good choices would be. I'm not going to spend a whole lot of time on this, but I do want you to think about, like, as I type this into my calculator, either again in Desmos or with your own graphing calculator, instead of h of t and using letters t, we would have written y equals negative 16x squared plus 64x plus 80. And so when we think about our x min, our y min, our x max and y max, we're going to leave the x max and y max alone right now. But I want to talk about your x min and your y min. We've used the letter x to replace the letter t, and we know that t stood for time, and we know we can't have negative time, so we know that the smallest possible x value we could come up with would be a 0. And if we think about what y represents, y is replacing h of t. H of t stood for our height. This one just talks about an object. It doesn't specifically say what it is, but we know that an object cannot have a negative height. So typically, our y min, we always make 0. So it's asking us to label and find the actual values. And again, kind of noting, I don't think these are in the same order as the previous one, but it's asking us where the object is launched from, the y-intercept, the max time and height of the object, which is found using your vertex, and when the object hit the ground, your x-intercept. So what I'm going to do on this first slide is just do a quick sketch. And we know that it's launched from an initial height of 80 feet. And so I can come here on my graph and say that this is 80. And then I know it's going to be a parabola, so it's going to go up and it's going to come back down. I don't know how long it's going to take, but I can actually answer part A. It says where the object is launched from, so that is our 80 feet. Again, we can see this in our equation as well. That is our 80, so it's always that constant in our equation. Then the max time and height of the object, and so that's going to be letter B up here. And so I don't know the coordinates of that point at this time, but we'll just make a note of it on our graph. And then for letter C, it wants when the object hits the ground, our x-intercept. And so this point here would be our answer to letter C. So just making some notes there. But to actually answer parts B and C, we're going to need to look at the graph. And so what I've done on the next slide is I have typed this equation into Desmos and graphed it for you. And again, you're welcome to open up Desmos and try this with me. Also, if you have your own graphing calculator, you're welcome to graph it there as well. And then we can compare those graphs. So the tricky part about doing this in Desmos is I've created the table for you as well, but unfortunately the whole equation does not show up. So I'm going to go in here now and add on that plus 80 just so you can see the whole equation. Again, I did type the whole equation in, but was not able to answer all of those questions. So again, I'm going to go through and label all of our answer choices. We said the answer to letter A was right here, and that was 80 feet. The answer to B was the maximum time and height of the object, which is looking at your vertex. So this was letter B. And the coordinates of that point, if you look at the graph here, are 2, comma, and then it's kind of hard to see on the graph, which is why I included the table. So this part B would be 2, 144. And we'll fill these answers in on the next slide. I just copied it over. And then part C asked us for when the object hits the ground, and that's your x-intercept. So that this point here, and that point, its coordinates are 5, 0. Notice you can also see these 3 points in the table. Here we have our y-intercept, 0, 80. Our vertex was at 2, 144. And our x-intercept was at 5, 0. Now again, I strategically picked values for the table. Again, if we were in the classroom, I would spend some more time with this, but having to do this through remote learning, this is kind of about the best I can do. All right, so let's go back to that question. Again, we had already answered the first question. It was launched from a height of 80 feet. And then it wants to know the maximum time and the height of the object. Again, that was our vertex. And we looked and saw that the time, that would be the x coordinate. So the maximum time was 2 seconds. And then the maximum height was the 144 feet. So there were 2 parts to that question. And then letter C, when the object hit the ground, the x-intercept, that was after 5 seconds. All right, let's take a look at another example. Number 2, at a festival, pumpkins are launched with large catapults and air cannons. In one launch, the height of a pumpkin in feet above the ground after t seconds is modeled by f of t equals negative 16t squared plus 100t plus 12. Again, like I mentioned before, your x-men and your y-men are going to be 0 because we do not have a negative time or a negative height. Again, if we're going to type this in to Desmos or our graphing calculator, we will use y and x. So negative 16x squared plus 100x plus 12. We can do a sketch. We know that that initial height is 12. And the reason I know that it's 12 is because it's represented by the constant. And so I can come over and sketch my picture. And again, just a rough sketch. It's got to go up and come back down. So this point here where it starts was 12. So we can go ahead and fill in part A. It was launched from 12 feet. The max time and height is going to be up here at the vertex. And then the pumpkin hits the ground here at letter C. Once again, I'm going to put this in Desmos. Take a look at the graph. Again, I've already gone through and figured this out for you guys. So let's take a look on the next slide. Once again, the Equation was cut off, so I'm going to fill this in first. So that was plus 100x plus 12 was our equation, so since it does not all show up. So our answer choices, again, we had already mentioned that this was letter A, my initial height. Part B wanted the vertex, so that was the maximum height and what time it occurred. And then letter C, the last part, was asking for the the X-intercept, so where it hits the ground. And again, I've already labeled each of those points. And that's the nice thing about Desmos is you can go in and click on certain points. It won't let you choose every point, but some of those key points. Again, I made a table again so you can see some of that information. We can see that y-intercept here was 0, 12. We can see our vertex here. But the one thing we can't see is we can't see that x-intercept. But you might notice that it would have to fall somewhere between 6 and 7. And the reason I know that is because if you look at the height goes from a positive 36 to a negative 72. Therefore, it went below ground, which I know doesn't make a whole lot of sense, but therefore it had to be 0 at some point in between. So even though we couldn't see the exact value, we know what the what two integer values that the x-intercept would have to fall between. Okay, so going back to our questions, again, we had already answered the first one was 12 feet. The maximum time we saw on the graph was after 3 seconds. And that was at 168 feet. And then it hit the ground after 6.368 seconds. All right, let's look at another one. So this time we're talking about a volcano. It says a volcanic eruption blasts a boulder upward with an initial velocity of 240 feet per second. Just a reminder that initial velocity is always going to be the coefficient of the t term or the x term, so that linear term. And then it gives us that equation, h of t equals negative 16t squared plus 240t. Again, just a reminder that negative 16 is the effect of gravity. I didn't talk about this earlier, but the reason, if you think through it, hopefully it will make sense to you. It's a negative number because gravity pulls an object down, so it's taking away from its height. So letter A says, how long will it take the boulder to hit the ground? So if we think back to the examples that we've done before, we're going to be looking there for the x-intercept. Part B, what was the highest point the boulder reached and at what time did this occur? So there we're going to be looking at the vertex. And then how high was the boulder after 5 seconds? And that one tells us to look in the table. We might be able to see it from the graph as well, but that's just going to be some point on the graph. So again, it's when our x is equal to 5. All right, so let's take a look at the graph that I created using Desmos. Notice this table was a little larger than the previous ones, but I stopped after 10 because it was getting so large. Once again, I had trouble showing the whole equation. It just cut off the x there. So negative 16x squared plus 240x, I'll stick that back in there. But again, those questions that it asked us to find, letter A, these were in a different order. Again, that one was, when will the object hit the ground? So that's going to be over here at my x-intercept. Letter B asked for, when does it reach its maximum height and what is the maximum height? So that's that black dot that I've clicked on. Notice this time that does not show up in your table. That was something that I had to find on the graph. And then the last part, it was asking us for the height after 5 seconds, and I clicked on that point, which is here. 5, 800, but again, I had mentioned looking at your table, so there's that 5, 800. Again, you cannot see the x-intercept because my table did not go, but if I had continued that table, then we would have had a 15, and then beside it there would be a 0. I just was not able to show all of that information. You may have noticed in this example that we don't have a constant out here, and that is because for this object, it was launched just straight off the ground, so our initial height was 0. So just trying to make some connections as we look at the different examples. All right, so on the next slide, we'll go back through those questions and record these answers. Again, using the information I found from the graph and table in Desmos. So how long? It took the boulder 15 seconds to hit the ground. The highest point the boulder reached, so that was your y coordinate, so that's 900 feet, and it took 7.5 seconds for that to occur. Remember that this boulder was launched from the ground, so maybe that makes sense to you, that if it takes 7.5 seconds to get to the highest point, then it should take 7.5 more seconds to hit the ground. And we do notice in part A, you think about 7.5 plus 7.5 does give us that 15 seconds that the boulder was in the air. Again, this is only the case because it was launched straight from the ground, not with an initial height other than 0. And then the last question, it asked for how high the boulder was after 5 seconds. And again, I showed you that as a point on the graph, but also I referenced that in the table, and that height was 800 feet. All right, I have one more example, and then I'm going to give you a couple practice problems to do. Number 4 says, Leo throws a rock upward from the top of a 50-foot cliff. The rock lands at the base of the cliff. The rock's height above the base of the cliff after t seconds is represented by f of t equals negative 16t squared plus 64t plus 50. Again, just reiterating that initial height, that 50-foot cliff is that constant. That negative 16 is going to be your gravity, and the 64, if you remember from the previous examples, that is your initial velocity. So that's how fast Leo threw the rock. So letter A, what is the rock's maximum height above the ground? Again, we'll need the graph for that. When does the rock reach its maximum height? When does the rock hit the ground? When is the rock the same height as the initial start? And what is the height of the rock after 3 seconds? So again, I cannot answer any of these questions just based on the equation. I will need the graph and possibly the table to answer these. So let's look on the next slide at where I've entered this information into Desmos. So we have our equation, which got cut off, so negative 16x squared plus 64x, and then we had our plus 50. So letter A asked us the maximum height, and that's going to be up here. So letter A is that 114. Letter B asked us when the object reaches its maximum height. So that's your x coordinate. So we're taking that and kind of splitting it into 2 separate questions for this one, just to kind of make sure you're seeing the difference between the two. So letter A wanted the maximum height. Letter B wanted to know when the object reached that maximum height. Letter C asked for when the object will hit the ground. So again, that's our x-intercept down here, so the 4.669. Again, that is not something that we're going to be able to see in the table, but we can see that between 4 and 5 seconds, that our y values go from a positive number to a negative number. Therefore, they will have to be 0 somewhere in between those and we see that on our graph. Letter D, this was a new question we had not seen before. It asked about when will the object be at the same height as it was initially. And so I'm going to kind of highlight these for you. Here was the spot of our initial height, and we see that it was at a height of 50. So if I come across, we see that once again, after 4 seconds, we are at that same height of 50. So I was able to see it in the graph. Also, it shows up here in our table. So 2 different ways to find that. And then lastly, letter E asked for the height after 3 seconds. So I have that labeled here. I clicked on the point for 3 seconds. Again, you can also see it in your table. So on the next slide, we will fill in the answers to those questions. So the maximum height was 114 feet. That occurred after 2 seconds. It hit the ground. Again, we had to use the graph to see this. After 4.669 seconds. It was the same height as that initial start of 50 after 4 seconds. Again, we were able to see that both in the graph and the table. And then the same thing for letter E. I showed you that value in the graph and the table. After 3 seconds, we had a height of 98 feet. Hopefully this has been enough examples to kind of give you an idea of how we work with projectile motion. On the next slide, you're going to have a chance to do some practice. Okay, so this is time for you to practice. Here's an example, and you've got quite a few questions. So on your paper, you can number 9 through 20. It says the following is a graph of an object that has been thrown into the air from the ground. It shows the height in meters of the object over time measured in seconds. So again, at this time, I want you to press pause, work through these questions, and then when you're ready to continue, press play, and we will go through these. Again, this is a pretty basic graph, so there's going to be some estimates. So again, our answers may not be exactly the same, but if yours is close, that will be fine. So again, at this time, press pause, work through these, and then when you're ready, press play. Okay, so we're going to continue now. Again, if you need more time or forgot to hit pause, please do so at this time. All right, so for number 9, it says, what is the maximum? Remember, the maximum is at the top. So to me, it kind of looks like it's right there. Not quite 5 seconds, but pretty close to it. So I'm going to say that is 4.9, and then it doesn't reach all the way up to 120. We're counting by 20, so I'm going to call that 118. So if you had something similar to that, that's fine. Your y-intercept, again, that's the point where the graph crosses the y-axis. So that's going to be here. And the coordinates of that are 0, 0. The x-intercepts, well, one of the x-intercepts we just listed, because that x-intercept is the same as the y-intercept. And then the other x-intercept would be where it touches the ground. And again, that's not quite 10, it's a little bit before 10, so I'm going to call that 9.8. So a little bit before 10. The axis of symmetry, so this goes back to Unit 7. Remember, your axis of symmetry is the line that cuts your parabola in half, and it always goes through the vertex. So I'm going to sketch this here as best I can. And so it's a vertical line, so its equation is x equals, and again it's the x coordinate of the vertex, so 4.9. It wants to know where the interval is increasing, so I'm going to use my highlight feature for this. So again, just read left to right. We're walking along, we hop on our graph, and we increase. And that happens from the time the graph starts till we reach that maximum. And I'm just going to use our interval notation. So that is from 0 up to 4.9 seconds. And then after it increases, then it starts to decrease. So on the other side, again, I'm going to use the highlight feature. We're decreasing on the other side. So that occurs from 4.9 until the object hits the ground, and again I estimated that to be 9.8 seconds. All right, next question is your domain. Your domain are your x values, and so we want to look across the x-axis. Hopefully these highlights aren't going to be too dark. So your domain are your x's, and so my domain is going to be this region here. So for my domain, that's going to be from 0 to 9.8. And I use brackets this time because we're including those. Again, that's not super important right now. That's something you will work on in your later math courses. And then your range, remember let's label this, your domain or your x. And then for your range, we want to do our y values. I think I'll use blue for this one. So we're going to use our y values. Again, I'm going to use my highlight feature. And I want to find my y values. And so we're looking at those. Again, it doesn't go all the way to 120. That may look like I went a little too high. And I think I estimated that was up to 118. So we can say our range is from 0 to 118. All right, the ones that are most important to me pertaining to this lesson are the questions at the bottom, talking about the actual connections to the problem. So 9 through 16 I felt like were more review, which is good for us to do. But for number 17 it says, what does the maximum of this graph mean in the context of the projectile? It says discuss both the x and the y. So for number 17, we need to go back and look at question 9. So we had the 4.9 and the 118. So what we could say here is at 4.9 seconds, the object is 118 feet high. So that takes into account both the x and the y. So again, the x coordinate is your time, your y coordinate is your height. All right, next question. For number 18, it says, what does the y-intercept mean in the context? Again, your y-intercept is number 10, and your y-intercept is going to show you the height of your object, the initial height. Number 19, what do the x-intercepts represent? And our x-intercepts we listed in number 11. These are the times when the object was on the ground. And so again, the reason there are 2 of those is because the object was launched from the ground, it goes up in the air, and then it comes back down and hits the ground. And then number 20 is a little weird. It talks about the practical domain and range for this situation. And that keyword here is practical. And we listed the practical domain and range. As we know, if we graph this in our calculator or in Desmos, the graph is not going to just show this window. It's going to keep going unless we adjust it. So that practical domain and range are the ones that make sense. So they're going to be the same as what we wrote in number 15 and 16. So our practical domain, again, no negative values. So that's going to be from 0 to 9.8. And that practical range is going to be from 0 to 118. Again, if we were looking at that graph and we did not change our window, we could see negative numbers for our domain and for our range, but that would not be practical because we know there is no such thing as negative time or a negative height. Again, if you have questions on any of these, please don't hesitate to reach out to me. On our next slide, we have one more example for you guys to work through, and then that will be it for today. So for this one, it says the graph to the right shows Juliet throwing her locket necklace out of her bedroom window to Romeo. Don't judge, I didn't make up this problem. Number 21 through 24, so picking up where we left off. So on your paper, if you will write those numbers down, press pause again, answer these questions, and then when you're ready to continue and check your answers, press play. So again, at this time, please pause the video. Okay, at this time, we're going to go through the answers. If you're not finished, please press pause. Once again, this graph is not super detailed, so my answers are going to be somewhat of estimates. For number 21, it says, what interval is her necklace above 90 feet? Just a reminder, intervals are X values. So we're looking for this section of the graph here, because that is where it is above 90 feet. And they've actually labeled these for us, so we can see that our graph was at 90 feet after 0.4 seconds, and again after 1.6 seconds. And so for letter A, we can say from 0.4 comma to 1.6, so using that interval notation. Number 22, what is the maximum height of the necklace and when does it reach this height? So for this one, it's going to be the kind of that tip-top spot right here, so that vertex, our maximum. And again, for this one, I just had to kind of estimate. For this one, I said that it looks kind of close to maybe after 1 second. And I estimated that to be 95 feet. So the maximum height was 95 feet, and that happened after 1 second. Again, if yours is slightly different, that is 100% okay. We're just having to do an estimate. What is the y-intercept and what does it mean in the context? So again, your y-intercept is here. Thankfully, this one's easy to read. My y-intercept, just a reminder, that is an ordered pair, so 0, 80. And again, the initial height would be 80 feet. So Juliet is 80 feet above the ground. So no climbing out the window. All right, and the last one, 24. What is the positive x-intercept and what does it mean in the context of the situation? You may have thought that question was a little weird because we're like, what do you mean the positive one? Because in the graph, I only see one x-intercept. So that x-intercept I'm seeing is right here. So once again, we're just going to estimate, and I'm going to say that looks to be after about 3.5 seconds. And because it is an x-intercept, I'm going to write it as an ordered pair. So 3.5 comma 0. And as far as the meaning, that means the object will hit the ground after 3.5 seconds. And again, this time she was throwing her necklace out the window. Well, I hope this has given you a little bit of clarity as to what we can use quadratic equations for in the real world and what the different pieces of these graphs represent. Again, we spent a lot of time back in Unit 7 with the vocab so that knowing eventually we would be able to do these real world problems. So here is your homework for this week. We changed it up a little bit. Instead of doing a Canvas quiz, we have a Desmos activity for you to complete. Please make sure that you sign in through your Wake County Google account. You will go to student.desmos.com, and our code for our class is KKTQ3J. It is important that you use your Wake County account so that your name will populate. So when I go in, I can see how you guys are doing. The second thing is to please check PowerSchool to make sure that you're passing S1 and Q3. I anticipate information coming out this week about how grades will be calculated. So I want to make sure that everyone is set for all instruction that happened before school was dismissed. So again, please email me. I've put my email address again at the bottom. I've sent numerous emails, but I'm not getting a lot of response. Hope you guys have a great week. Take care, and please let me know how I can support you.